Hello, hello. Okay. Before we get started, can our third speaker, Andrew Kumar Tyagi, if you're here, can you come up real quick? All right, no worries. Okay, so let's get the session started. So this is a session called VA for ML. The original session chair is Timo Rapinski. Unfortunately, Timo lost his voice last night, so I'm stepping in as the backup option. So my name's Rimko Chang. I'm an associate professor at Tufts University. And I'm going to have Camelia Brumar, who's going to be my assistant sessions chair. She's going to help monitor questions on Slido and help keep time. So to get things started, we have 5 papers in this session focusing on using visual analytics techniques to understand and manipulate machine learning models. The first paper is called GNN Lens, a visual analytics approach for prediction error diagnosis of graph neural networks. And the presenter is going to be Zihua Jin. And the authors are from HKUST, the Hong Kong University of Science and Technology. All right, can you get set up? Yeah, and while Zihua is getting set up, if you have questions, please write them into Slido, and we'll be reading the questions off of them.
Sorry. The slide. Oh, okay. So, yes. Hello, everyone. I'm Zhihua Jin, a fourth-year PhD candidate from the Hong Kong University of Science and Technology. Today, I will present the paper GNN Lens, a visual analytics approach for prediction error diagnosis of graph neural networks. This is the joint work with the Singapore Management University, Harvard University, Bloomberg, and IBM. Graph neural networks can be used in various kinds of applications with graphs. For example, in social networks, nodes represent users and edges represent followers. According to the social networks, graph neural networks can be used in the classification of users types. In citation networks, nodes represent papers and edges represent citations. According to the citation networks, graph neural networks can be used in classification in the papers types. Graph neural networks is neural networks taking graph structure and node features as inputs. Based on neighborhood aggregation idea, it can utilize the graph structure and node features information. In this example, considering target node 0, we can aggregate information from its neighborhood using graph neural networks. GNN seems like a black box. When diagnosing GNN, it is hard to identify the source of errors since details are hidden from the model developers or model users. Therefore, the development of a GNN is a typical trial and error process. To effectively analyze GNNs, it is crucial to properly link the topological data, high-dimensional features, and prediction results. We would like to seek a visual analytics approach to address how to help model developers and users identify causes of misclassified nodes and find error patterns in GNN prediction results. Previous works have proposed techniques to explain GNN model prediction results. They mainly focus on instance-based explanation. For instance, LRP identifies the reason of classification through salience, and GNN explainer identifies important subgraph for GNN predictions. However, they fail to provide ways to analyze the reasons for error classification in a group of nodes and extract error patterns in the GNN prediction results. To address these limitations, we provide a visual analytics system, GNN Lens, to assist model developers and users in the identification of error patterns by enabling users to inspect the overview of low-level matrix distribution and correlation. Users can further analyze the causes of errors by inspecting the details of graph structure and node features information. We define a set of policy models and low-level matches to help analyze the influence of the graph structure and node features on GN prediction results. Policy models include GN, WUF, and NLP. Matches include graph structure-based matches and node feature-based matches. Similar to the evaluation study when evaluating GN models, we define two policy models which have the same model architecture as GN but are trained using different input data. For GN results using features, it only considers graph structure. For multi-layer perceptron, it only uses node features. They can reflect the influence of graph structure and node features respectively. To help users check whether the one-hot neighborhood exerts influence on the GN prediction results, we define center label consistency rates, which measures the consistency between the current node label and the label's label. For example, in this example, for node A, 3 out of 4 labels are the same as the node A, so label consistency for node A is 0.75. Similarly, we can measure the consistency between the current node label and the label prediction results, which is calculated as label prediction consistency. To investigate the influence of training nodes distribution or model training from the perspective of the graph structure, we calculate the nearest training nodes label distribution. For example, for node A, 3 out of 4 nearest training nodes are with the same label as node A. Then label 1 occupies 75% and label 2 occupies 25%. In order to help users quickly capture the dominant information of the nearest training node's label distribution and further diagnose the causes of errors in GN prediction results, we define the nearest training node's dominant label consistency as whether the nearest label is consistent with the current node label. For example, label 1 occupies most in the nearest training node's label distribution, then this value is set to true. Similarly, to reflect the influence of training node's features on the model prediction results on the current node, we can define the label distribution of the top k training nodes with the most similar features. In this example, k is ambiguously set to 5. Then label 1 occupies 60% and label 2 occupies 40%. For top k most similar training node's dominant label consistency, it has a similar definition with the nearest training node's dominant label consistency. For example, label 1 occupies most of the above distribution, then this value is set to true. The interface of GNNs consists of 5 main views. The control panel allows users to load the specific datasets and inspect the specific speaking of the datasets. The parallel sets view enables users to see the distribution of low-level matches. They can also inspect the correlation between those matches. The projection view presents a set of 2D projections of the selected nodes according to features summarized from different perspectives, enabling users to extract potential clusters of nodes. Different node glyphs are designed for presenting different aspects of information in the nodes. Hierarchical clustering is applied to aggregate similar nodes to reduce visual clutter. The graph view shows the information of the whole graph. Users can also interactively explore the topological structures of a specific node. The feature matrix view shows the selected node's feature information. It further enables users to check the detailed information of individual nodes. We demonstrate one case study with the expert E1. E1 chose to inspect the GCN model that is applied to the Amazon photo datasets. When exploring parallel sets view, E1 found that the model misclassifies most of the nodes in class 7. E1 found that most nodes with label 7 have false values for nearest training nodes' dominant label consistency and top k most similar training nodes' dominant label consistency. E1 speculated that this is the reason for misclassification made by GCN. E1 selected only classified nodes with the label 7 by GCN in parallel set view. From the parents of training nodes structure influence and feature influence in the projection view, few nodes of label 7 appear in the label distribution. It confirms the patterns found in parallel set view. E1 found that 3 training nodes were also misclassified. Iwan selected them and then selected one of the rows in the graph view. Iwan found that a large number of labels have different labels for this row. Iwan also observed that for no gifts, the GCN WF prediction results is consistent with the GCN prediction results. In the feature matrix view, this row has many overlapping features with the talking mode similar training nodes, while most of those nodes have different ground truth labels. This observation supports that it is very hard for GCN to correctly classify the test nodes with a strong influence of structure and features of nodes with other classes. Increasing the loss on training nodes with label 7 is a way to resist the influence from other nodes for nodes with label 7. In conclusion, we present GNNs, a visual analytics system to help model developers and users understand and diagnose GN model prediction results. And there are 4 visualization components linked together to support users in analyzing GN models simultaneously from multiple angles and extract general error patterns in GN prediction results. There are many aspects to extending GNNs. For example, it can be extended to other graph-related tasks like link prediction and graph classification. Dynamically inserting nodes and edges to see the corresponding change in GM prediction results can be extended. Customized data, including multiple relations or edges, have features or customized metrics to inspect the relationship between them and the model performance can be further supported in the future. We also collaborated with the DGL team to integrate our tool with the DGL library, which is widely used by GM model developers. Through the integration and providing detailed tutorials, GNNs is easier to use and gains broader impacts in the community. Thank you for your listening. You can also use this code and demo links to fully reproduce GNNs. Thanks.
All right, we have a question from Slido.
So, what are the typical error patterns that could be detected with this tool?
Yes. So firstly, we display the GCN the prediction result, whether it is correctly in the parallel set view, and then there are multiple dimensions to display many metrics, and then we can investigate the misclassified loss, the relationship between them and the corresponding metrics. For example, in here we define multiple metrics. Then we can investigate what error patterns it may have. Yes.
Cool. Are there other questions? I'd like to encourage people who are here to just be able to come up, use a microphone, and ask a question. Let's do this old school style. Sorry, you have to come up to the microphone, otherwise it's not going to get recorded.
Hi, so...
Can you say your name and affiliation?
Hi, I'm Christina. I work at Amazon. I'm interested in the last thing you mentioned about how your code is extendable to work on graph classification tasks. How much work would that entail?
Okay, you are asking how extending the current system to the graph classification task, right? I think that it can be a very good future directions to support it. In terms of our current system, we support only the transductive classification task, and then if to support multiple graph classification tasks, we can also consider the training graphs as opposite like the training nodes here, and define metrics, measure the similarity between the training graphs with the test graphs. Then we can also use this system to support the analysis of the graph classification task.
Okay, thank you.
All right, if there are no more questions, let's thank the speaker again. All right, Our next presentation is a remote one or virtual one, pre-recorded. The title of the paper is Visual Analysis of Neural Architecture Spaces for Summarizing Design Principles. The paper will be presented by Jun Yuan from Tsinghua University.
Neural architecture spaces for summarizing design principles. This is a joint work with Meng Chen, Feng Yuan, and Shi Xiang. Recent success in artificial intelligence largely benefits from better neural network architecture design. Many neural architecture search methods have been developed to automatically select a well-performing architecture in a neural network architecture space. However, it is usually hard to understand why the selecting architecture achieves well performance. To tackle this issue, recent work focused on summarizing design principles that describe how specific structural components influence the performance. They have been shown to be useful in designing more explainable architectures with better generalization ability. The key for summarizing design principles is to understand their structural distances. There are two main challenges in summarizing design principles from an architecture space. First, there can be tens of thousands of architectures in an architecture space, leading to the calculation of millions of distances, which brings scalability issue. The key to tackle this is to formulate the calculation as an all pairs shortest path problem and leverage existing acceleration algorithms. Second, it is non-trivial for users to identify the architectures of interest and analyze them in context. Thus, an architectural visualization is developed to illustrate the architectural relationships. Accordingly, our system consists of two modules. The architecture distance calculation module efficiently calculates the pairwise distances between architectures. The visualization module facilitates the identification and comparison of the architectures of interest to understand which structural components are beneficial to the performance. First, we introduce the architecture distance calculation module. We use a small example to illustrate the basic idea of the architecture distance calculation. Given 5 architectures, they are modeled as directed acyclic graphs, and we adopt graph at the distance to measure their structural distances. For efficient calculation, we first build the architectural graph to describe their one-hop neighbor relationships. Each node represents an architecture, and each edge connects a pair of architectures with only one edit operation difference. Then, we calculate the pairwise distances on this graph. For example, the distance between x and y is 2. The distance between x and z is the shortest path on this graph. So it is 4 in this case. The pairwise distance calculation is thus formulated as an all-pairs shortest path problem. The question is that how to efficiently solve this problem. We observe that the architectural graph is sparse and the edit distances are discrete. Therefore, we decompose this all-pairs shortest path problem into a set of single-source shortest path problems. They are then solved by an accelerated dissection algorithm, and the time complexity can be reduced. Next, let's move on to the visualization module. As there can be tens of thousands of architectures in a space, we first construct an architecture hierarchy based on their distances. When exploring a certain level, we employ a cluster-aware sampling strategy to sample a few architectures for visualization. The sampling strategy aims to maintain the relative sizes of clusters while preserving smaller clusters. With the sample architectures, we design an architectural visualization to help users identify the architectures of interest and provide useful context for comparing and analyzing them. Here, a circle represents an architecture, and the color encodes its accuracy. The darker the circle, the higher the accuracy. We also select some representative architectures from each cluster and illustrate them with summary glyphs and structure glyphs. The architectural visualization is expected to illustrate the similarity relationships between architectures. First, it should preserve the global cluster relationships. In particular, Similar clusters should be placed nearby and vice versa. Besides, it should also preserve the local neighborhoods of individual architectures. For example, the architectures with a single identity layer connecting the input and output should be placed at neighboring positions. To preserve the global cluster relationships, we utilize the widely used force-directed layout to place the architecture clusters. Here, we focus on introducing the circle packing layout with glyph placement to illustrate the local neighborhoods of architectures. In the circle packing layout, each architecture is represented as a uniform circle, and each summary glyph takes up the space of 7 compact circles. Therefore, the circle packing problem is transformed into a hexagonal grid layout problem and formulated as a quadratic assignment problem. It aims to minimize the sum of distances between neighboring architectures in the layout. Since it is NP-hard, this problem is approximately solved by a greedy strategy. We conducted 2 case studies on 2 next benchmark datasets. 101, which contains over 400,000 architectures, and 201, which contains about 15,000 architectures. 8 design principles are summarized from these 2 datasets. Here we used a simple case to illustrate how users can summarize design principles with ArcExplorer. From the overview, the user identified a cluster with many well-performing architectures. They only used convolution layers. He then zoomed in to examine this cluster in detail and found that the well-performing architectures were mostly located in 3 subclusters. The subcluster at the bottom left used fewer convolution layers, but contained a comparable number of well-performing architectures. Selecting these subclusters and comparing them in the table, he found that the architectures with less convolution layers had more skip connections. With further examination and analysis, he summarized that dense skip connections are beneficial to model performance. Based on the summarized design principles, we collaborated with an expert to manually design an architecture from NestMatch 201. We compared the proposed architecture with the next searched best performing architecture on 7 image classification tasks. The proposed architecture has achieved better or comparable accuracy on all datasets. This demonstrates the effectiveness of the design principles. Moreover, we combined the design principles with a state-of-the-art nest method to evaluate its effectiveness in improving the search efficiency. Results demonstrated that the hybrid method can reduce about half of the computation effort while keeping the accuracy of the searched architectures. To sum up, we developed ArcExplorer for visually summarizing design principles from a neural network architecture space. In the future, we plan to explore recommendation functions to help derive design principles more efficiently. It is also worth to study how to integrate our tool into the search process of nest algorithms to further improve their performance. Last but not least, we aim to generalize ArcExplorer to consider more factors such as training hyperparameters and data distribution. Thank you for your listening, and I am happy to take any questions.
All right, we have a couple of questions. Oh, hey, there you are. Can you hear us? Yeah, you're muted, by the way. Always happens.
Hello.
Great.
Hello,
Excellent.
everyone.
Hi. We have a few questions on Slido.
Okay.
So the first question is, can you elaborate on how to efficiently calculate all nodes' shortest paths? The naive solution seems quite expensive.
Actually, we built a neighbor graph for all the architectures in the architecture space. Since the architecture space used in our experiment is quite small, like NestMatch 201 only contains 15,000 architectures. So we can efficiently build an neighbor graph for all the architectures in this space, and each edge represents a one-hop neighbor relationships. And then we can leverage some existing all-pairs shortest path problems, existing solutions for the all-pairs shortest path problems. But we can observe that the neighbor graph is sparse, and therefore we can decompose this all-pairs shortest path problem into a set of single source shortest path problem and leverage an acceleration version distress algorithm to efficiently calculate the all-pairs distance of the nodes of all the architectures. Yeah.
Thank you. The second question is, how do you choose representative architectures to show in detail in your architecture overview? And did you get any feedback from experts about whether they agreed that these architectures were representative?
Okay, that's a good question. Actually, we have communicated with the experts that which architectures are the most concerned in the architecture space. Of course, they will be interested in the architectures of well performance. So the first criteria for selecting the representative architectures is that we will select the best performed architectures in a cluster, and then the representativeness of the architectures should describe how the characteristics of the architectures in this cluster. So we also consider using a subset selection problem based on the distances calculated in our data processing stage, and select some more representative architectures. But there is a constraint that the selected architectures should also be if above 90% of the its accuracy should be above 90% of the other architectures. So these architectures are better performing and more representative, and users and experts can analyze these architectures and to find what makes them become a good architecture and what improves their performance. Yeah.
Okay, so while I'm up here, can I ask Angel Tiagi to come up? Okay, you're here. Thank you. Okay, wait. Go ahead.
There is time for one more question. There is a question that says, I wonder how each architecture is represented. When comparing two architectures, do you differentiate between totally different operators or slightly different variations?
Okay, we represent each architecture as an directly acyclic graph, and as we know, a recent trend in neural architecture search is to search the cells in the architecture space and stack the cells to construct the whole architecture. So when we compare two architectures, we only compare the difference of the cells they use to construct the whole architecture. And in our experiment, and the cells are the blocks used in the cells are absolutely we will consider the parameters or the structure difference of the used blocks in the cell, but at this moment, since the current practice is to use different blocks to construct a cell in the architecture, so we can only measure the distance between the different blocks used in this cell, and this can be found in previous works in the machine learning field, and we only borrow their distance in our work. Yeah.
Thank you. There are a couple more questions on Slido if you want to have a look at those, but we're on time.
Okay,
Okay,
thank
let's
you.
thank the speaker again. All right. Our next presentation is in person. The paper is titled NAS Navigator, Visual Steering for Explainable One-Shot Deep Neural Networks Synthesis. And the presenter is Anjul Tyagi from Stony Brook.
All right. Hello, everyone. So today I'll be presenting my work on NAS Navigator. This is my work in collaboration with Kongshi and my advisor Klaus Miller from Stony Brook University. So the topic is NAS Navigator, Visual Steering for Explainable One-Shot Deep Neural Network Architecture Synthesis. So why do we need neural network architecture search? So the problem is designing a neural network is hard. And however, if you can get it right, the perks of getting a right neural network is really good. So as we can see in this image, the accuracy on IBISNet dataset of all these years on deep neural networks has been increasing because deep learning has been very successful. And this is an effort by so many experts in deep learning, and they've worked so hard to design these neural networks. And the problem is designing these networks manually is very expensive, and NAS basically wants to automate this problem. So if there's an automated way to actually get this right, if you can actually design a network without any human intervention, so that'll be a great approach to take. And we can simply use these networks for our data sets. This is one of the examples of his manually designed block of Inception V4, very famous convolutional neural network. So coming up with these ideas is not trivial. You need years and years of experience in deep learning, and that's what we're trying to automate with neural network architecture search. So talking about previous works, they've tried to solve this problem using many different ways. Reinforcement learning is one of them, where you have a generator network, which is a recurrent neural network in many cases, and then you generate child networks, evaluate their accuracies on data sets, and basically feed that back into the network with a reward function. So the network eventually learns to generate different child networks with higher accuracy, as you can imagine. Now, the problem with previous approach is it's really expensive because you have to generate different child networks and evaluate them again and again, train them first and then evaluate them. So one improved method is one-shot learning. In this case, what happens is you only train once. So there's a big repeated network. So this network has different components, and it has several individual neural networks in it. So it's an oversized network, and many different components, when they're combined in a form of graphs, form an individual neural network in this whole search space. And what happens now is you only train this super network once, generate all the child networks. You don't have to train them again. You only evaluate them, get their accuracies, and you can use your original search idea to basically rerun the search in a better way. And the problem now is in a pre-trained network, you have to find the best path that gives you the highest accuracy. So we switch the problem, and the resource constraints now are very low compared to the original methods. There are also limitations comparing all these techniques to visualization perspective. So fully automated methods, as we saw, are very resource intensive. Also, one-shot methods lack explainability. We have a result, but we don't know how we got to that result. Also, we're not able to look at the search space of all these networks and which space is behaving good or bad compared to the original network we have. And also, there's lack of human-in-the-loop intervention, so we can't control the search. You design a reward function, and the search would basically take care of it on its own. So in this work, we present NAS Navigator. This is an all-in-one human-in-the-loop NAS system, which is fast compared to the automated methods, and it's also explainable. So we can visualize the search space and also make decisions to how to direct our search in some direction that we want to. So this is the interface for NAS Navigator. The main view here shows the SuperNet, the oversized network architecture, where you can zoom in and out and use pan to visualize different complete architectures of blocks in the network. And down here is the search space view that projects different candidate architectures onto a scatter plot. Very similar to the previous work we saw, we also use graph at a distance, and similar networks are placed closer to each other on this scatter plot. So this is a TSNE projection of the graph edit distance. Next up here is the candidate information view. What this shows is all the blocks in this oversized network. When we do the search, how important each of these blocks are in the network. These are shown in this candidate information view. We'll go over on that in a bit. And here is the loss chart. This basically shows the training process and how your oversized network, when you train it once at the beginning of the process, how the losses, validation loss and training loss are behaving, and is the network actually learning something from the dataset or not. Now we talk about visualizing the NAS search space with NAS Navigator. So user can basically choose any of the template networks of these supernets, oversized networks we have provided in the interface. You can load any of these templates. We have templates for ResNets, VGG, all these different famous convolutional networks. After loading, the search space view here shows the candidates and how they are scattered on this search space. So when you hover over any of the dots in this search space view, the components which are a part of that dot are highlighted in this final oversized network. So all these red outline blocks are actually the components which are considered on an individual dot in the search space. So training the supernet, sorry. So after we have loaded the interface, the search space view is populated. And so we can start the training of the supernet by clicking on this search space search button here, and which shows the updates in the loss chart. And eventually we can see how much accuracy, or we don't have to train the supernet to a high accuracy, but this loss chart basically shows you what performance would we get if we were to use this oversized network on any data set. So the goal is we have to filter candidates from this network and evaluate them, basically rank them against each other. So we don't want the supernet to be highly trained or highly efficient. We just want it to be good enough so we can rank these different candidates we filter from it against each other. And it's like all these candidates share the weights from this main supernet. So search space clustering and ranking. Once we have a trained supernet, we can start our evolutionary search algorithm, which iteratively samples candidates from the trained supernet. And as we can see here, the search space view is clustered as the search is progressing. So we cluster, we basically color all these candidates based on their evaluation accuracy as we validate them on our validation data set. So as you can imagine, eventually we'll have like a clustering in the search space formed after a few search iterations. Now you can do filtering operations on this search space. You can look at a good region or a bad region in the search space, and this operation would basically confine the future search iterations to focus on just this small region of the search space. So next candidates will only focus on this region. So that's human intervention. You can control the search, and you can also look at common blocks which were in this search space. So we provide 3 set operations to look at common regions which were part of this search space. You can look at union, intersection, and complement of these blocks to see what were the major contributors to why that particular search space was behaving in that way. Okay, so all of this is backed up by our evolutionary search algorithm. So let's quickly look at how this works. So we have initial networks A and B, the parent networks. They're generated. We start with randomly generating these bit masks. So all the blocks in the supernet, we randomly generate bits to start with a few candidates, A and B in this case. And what these bits means is if you have a set bit at a particular value, then that path would be included in that candidate. So here we have set bits for first and second, so 1 and 2 will be included in the child networks. So once we have these initial candidate networks, you generate fitness scores for all these paths. So initially they're all set to the same value. Now what happens as the search progresses, we evaluate A and B on our validation data set. So in this case, A was good, it has 85% accuracy. B was not that great, only 25% accuracy. So we can tweak these fitness scores of all these blocks based on these validation accuracies. So paths which were in B would go down, paths which were in A would go up. And next up, what we can do is use this as a distribution and sample paths from this modified distribution. So the probability of us ending up with useful paths would be more than compared to the less useful paths. So you can have these candidate networks in the next search and then generate a child network, which is the intersection of the paths in the father and the mother network. So that's how we progress the search, starting with random, and then it basically learns how to sample better and better paths from the super network. Talking about the results, we compared our search algorithm with a fully automated way without any human intervention. And these are the results. So we divided the categories into 3 parts. Human experts is basically deep neural networks designed by humans. NAS with more than 100 GPU days were initial NAS methods, and this is one-shot NAS methods with less than 5 GPU days. As you can see, our GPU resource usage is really low because you can control the search, and so validation GPU usage is reduced by a great amount. And we also don't have to train the supernet to that extent. And we get similar accuracy compared to the original methods. This is with human-in-the-loop intervention. So when you actually use NAS Navigator to control it, you can see NAS Navigator when used by experts, GPU usage is really reduced. You can use decisions to control the search, delete and modify components in the search space. So it's almost reduced by 50% compared to the fully automated methods. And we still get comparable accuracy to the existing fully automated methods this is on CFAR 10. Okay, so, sorry. That was it. Now talking about a few important contributions that we can take home from this work. So we presented NAS Navigator, which combines a one-shot automated approach with human-in-the-loop design. It's less resource intensive compared to the fully automated methods, and humans can control it. It's very easy to adapt, and experts and non-experts can take advantage of it and learn from the process. All right, thank you for your attention, and you can check out the code on this GitHub link, and feel free to reach me out with any questions on my email. Thank you.
Thank you for the talk. One of the questions that popped up in Slido is, since the process is largely automated and takes a long time, did you consider other modalities than a browser-based application, like a mobile application that the model builder can check intermittently, or adding email notifications when decisions need to be made?
Oh, I'm sorry. I feel like I can't hear you properly. Can you repeat the question? Sorry.
Absolutely. Since the process is largely automated and takes a long time, did you consider other modalities than a browser-based application, like a mobile application that the model builder can check intermittently, or adding email notifications for when decisions need to be made?
Yeah. That's actually a great idea. So it was, because it's a whole NAS process that you can intervene. You can basically, what we did was you can come back in an hour or so and check how is it going and then tweak it. If you're a system administrator, you can do that. But it's a great idea, so that'll be a good future direction to consider. Thanks.
Thank you.
All right, so I think that's all the questions on Slido, so let's thank the speaker again.
Thanks, everyone.
All right. Next, we have a remote presentation. The title of the paper is Vis, a visual analysis approach for identifying data heterogeneity in horizontal federated learning. The paper will be presented by Shumeng Wang, who is from Nankai University.
Hi everyone, I'm Shumeng Wang from Nankai University. Now let me introduce Vis, a visual analysis approach for identifying data heterogeneity in horizontal federated learning. This is a joint study from Nankai University, Zhejiang University, Central South University, and Graz University of Technology. In the real world, data are sometimes collected and stored in different clients. For instance, different supermarket chains have transaction data of customers who live in different places. Horizontal federated learning model can integrate distributed data by introducing a server. The server exchanges model parameters among multiple clients and synchronizes them into the parameters of the horizontal federated learning model. Since no data access is needed, federated learning can train federated model without privacy leakage. However, data distributed in different clients could be heterogeneous from the perspectives of statistical features and labels. For example, more younger individuals prefer to live in downtown instead of suburb. So customers in different places have different age distribution, which is statistical heterogeneity. Besides, in summer days, inland residents need caps to handle continuous sun exposure, while seaside residents prefer sunglasses to isolate harsh sunlight. Similar things lead to different results, which is label heterogeneity. These data heterogeneity issues affect the performance of federated learning model in different ways. Some are good and some should be avoided. As the client analyzed how to figure out the existence of data heterogeneity issues and know their impacts, and how to understand the effectiveness of federated cooperation. According to these questions, we have a goal to explore data heterogeneity issues from the perspective of a client. To achieve this goal, we discussed requirements with federated learning experts and summarize the following 3 requirements. First of all, clients analysts need to have a chance to know the existence of data heterogeneity. Second, client analysts need to compare local client data and other client data to explore data heterogeneity. However, client analysts are not allowed to access data in other clients. Instead, they can only have parameters of the federated learning model. To overcome information asymmetry, we have to construct local model and compare data in terms of model behaviors. Third, to further understand data heterogeneity and their impacts, client analysts need visual explanation on data features or accuracy drops. For the first requirements, we identify data heterogeneity from 2 perspectives. The first is the performance of federated learning models. Data heterogeneity will hinder the convergence of the federated model and harm its performance. Thus, performance indicators like accuracy and loss can reflect the existence of data heterogeneity. Besides, federated model iteratively integrates model parameters from client models. The data heterogeneity will lead to differences in model parameters submitted by different clients. Therefore, the significant parameter conflicts are also a signal of possible data heterogeneity. We design a parameter projection wheel to show parameter conflicts. The evolution of federated model parameters are delegated by a line with color gradient. The color encodes the communication round. To show the parameter conflicts, we draw arrows to show local parameter updates at each communication round. The color of the arrow encodes the cosine of the angle between the arrow and the green line in the high-dimensional space, which are the disagreements between the federated learning model and the local client. For the second requirement, we train a local model with local client data without parameter exchange. This model is called standalone training model. Given the same input, we can compare the outputs of the standalone training model and the federated learning model. Brackets with consistent and inconsistent outputs can be identified. The following analysis will focus on the inconsistency. To extract specific heterogeneity issues from inconsistent brackets, we employ a hierarchical clustering approach. Traditional hierarchical clustering is based on Euclidean distance, where records that are close together are preferentially clustered together. However, inconsistent records may be mixed with consistent records. Considering the existence of consistent records, we should actually aggregate A and C together instead of A and B. So we instead use rank-based measurement. To calculate such a measurement, we first calculate the rank of a record to the others among all records, including consistent records. Then we construct a symmetry distance measure by multiplying the mutual ranking. Now, A and C can be first clustered together. To further support visual exploration of labels and dimensions, we deconstruct high-dimensional data by CCPCA. According to the first two CPCs of CCPCA, we identify the best projection directions that can differentiate inconsistent records and others. Also, according to the first two CPCs, we calculate weights for each dimensions so that users can figure out how a dimension contributes to inconsistent records. Considering some heterogeneity issues can be solved during the training process, our system supports users to track the evolution of heterogeneity issues by annotating inconsistent records. Flexible joint operation is supported to select records. The above process can be summarized as the three-stage workflow. First, we monitor the learning process to know the existence of heterogeneity issues. Second, we compare model output to extract heterogeneity issues. And third, we examine heterogeneity issues by visual exploration. In the case study, we trained a federated learning model with 0 to 9 handwritten digit images. Our local client has images of partial digit zeros and digit ones. Other 9 clients have different pairs of digits. In the communication round 40, Vis help us identify the following data heterogeneity issues, including typography digit ones, left-leaning digit ones, digit 1 with an extra dot, giant digit zeros, and theta-like digit zeros. All of these records are misclassified by the federated learning model, and the standalone training model can classify them correctly. Therefore, we should suggest other clients to collect more pictures of digit 0 and digit 1 to optimize the horizontal federated learning model. In order to verify the effectiveness of the proposed clustering approach, we compare rank-based clustering with the traditional clustering approach. It can be seen that under the number of clusters automatically recommended, the rank-based clustering approach can identify meaningful clusters, including the typography digit ones, but the distance-based clustering approach can only get scattered clusters. After setting the number of clusters to 100, the largest cluster identified by the rank-based clustering is almost unaffected, but the results of traditional methods are still very scattered. In summary, we have 3 contributions in this work, consisting of a novel visual analysis workflow, a context-aware clustering approach, and a visual system that integrates a suite of novel designs. Finally, I'd like to thank all my co-authors, and thank you for your listening.
Hello, can you hear us?
Yeah, I can hear you.
Excellent. We have a couple of questions on Slido.
Thank you for the talk. So the first question that came in on Slido is, are there any challenges or changes to the system that you would make to use the system to identify and mitigate adversarial attacks?
This is an interesting question, and thank you for this question. As I know, adversary attacks like poisoning attacks may also lead to heterogeneous issues. So through our system, Vis, you can also find some possibilities of your system is attacked by other clients, but you can hardly to make sure whether they are malicious or not. For example, there could be just data problem instead of they just put some bad data into the training system. So I think the main challenge is you can hardly judge whether it is an adversary's attacks or not.
Thank you. Another question is, what are some differences in federated learning training versus regular training?
The main difference, I think, is the privacy issues. Because federated learning care about privacy, so the data cannot be accessed from each client, which means you can hardly access the data on other clients. In the normal training process, you can just check each data records, but in federated learning, you can only check the data on your client. And in the federated learning, there is a server to communicate with each other and send parameters, update parameters with each other. So that's the main difference.
Thank you.
Mm-hmm.
All right, let's thank the speaker again. Our next paper is called DendroMap, Visual Exploration of Large-Scale Image Datasets for Machine Learning with Tree Maps. This paper will be presented by Donald Bertucci, who's from University of Oregon or Oregon State? Oregon State University, sorry about that.
Hello there. Okay. I should just mention that you people look like you're going to riot if you don't see a live demo. So there's going to be a live demo in this. So yeah, look forward to that. Okay. Okay, so my name is Donnie Bertucci, full name Donald Bertucci. I'm an undergraduate student at Oregon State University, and I will be presenting DendroMap. Okay, let's start with a little bit of a mind meld here, and suppose we have just this sea of image, this random structure of images. We have no extra metadata to slice this. Where are you going to really start to understand these images? I mean, even looking just slightly closer into this, can you really understand the different concepts within here? Can you get an idea of the number of that concept? And if you do have that concept, can you compare it to other concepts? And even just looking at some of these images here, like we have some fruits, we have an apple, you have to look to that image and then you have to look everywhere else. It's a pretty difficult process, even for this smaller number of images. And really where we're trying to look at is problems that extend this problem. So places where understanding the images is important, for example, if you're training an image classifier, some model, for example, neural network, understanding the data is quite important. And you could imagine, for example, if you did have this defined human structure of metadata where you could slice all these different interesting slices. For example, if you could find all these small mini dogs that were white, you could say, push that through the model again and say, this is doing pretty terrible compared to all these other really nice things. You could potentially make some better decisions before training and after training. But as you know, in terms of machine learning data sets in general, we can't really expect all this nice metadata. So for now, we just have this random structure, which I hoped you got from the beginning that it's pretty terrible to visualize. So we could really just automate this just a step further and try to understand the different clumps and different similarity. So we can do that. You can add, for example, a local structure preserve local similarity here with like t-SNE, and to make it comparable to the beginning, we can put it into a grid structure. And just from this, you can see that things are clumped up. You have a place to start, and within each group here, each stuff clumped up, you can interpolate through those and look through the concepts within there. And to put things into perspective, what we did with DendroMap is to add another step of structure here, which is hierarchies of similarity. So before, maybe you were implicitly looking through t-SNE, trying to find different hierarchies of concepts within certain groups. But here we're just explicitly doing that, and you get all these other nice properties in terms of visualizing a large number of images here. So that's what DendroMap is. Of course, I'll be getting to the live demo shortly, but it's also the sidebar here. So we know extra information as well. For example, with image classification, we also know, was this mispredicted or not? So we could directly show that on the DendroMap, and we could also, because we also know the class information, we can visualize this class table here, which is somewhat analogous to a confusion matrix. So, right, before I get into the live demo, let me just give you some idea of what DendroMap actually means, because I think it's a pretty cool word. So DendroMap is dendrogram and tree map combined, where we have a dendrogram, which is a hierarchical structure, which we have groups of similar images. And just from the structure, you can see if this is our toy data set here, it immediately can just split into these animals and these machines and so forth, down to the images themselves. And to be totally honest, we go the other way. We go bottom up, we do hierarchical agglomerative clustering, and you get some other nice properties as well. And we directly translate this into a tree map, where we visualize the images on top. And the nice part about this is you can easily have summary overview, but also get more detail by going into a hierarchy. So for example, if I want to render a different portion of the tree, I could click on these different machines here, this node, and I could zoom into there, and I could visualize just those. And to give you some more information for how this actually works, in terms of directly translating this to the tree map, we have this parent node here. It's a local parent, in fact, and we have a whole node behind it, and these are colored by depth, and you could nest those by padding, and we use slice dice with the tree map because there's no reason not to when you're only laying out 2 nodes per hierarchy. And with all of that, we translate that into this hierarchical and zoomable tree map. So I have some examples here, but I'm just gonna go straight to the live demo because that's the most interesting part. Okay, let's get past this. Okay, so hopefully somebody in Discord can copy paste this link so maybe you guys can follow along. But I'll be going just to my locally hosted one because I'm assuming that we don't have internet. So just to start off, as you can see, this is the DendroMap and we have the sidebar here. And you could follow on, by the way. So here we just have an overview of this entire data set. And in this case, we're taking the ResNet 50 embeddings and we're hierarchically clustering those. We're kind of seeing what the model has learned at the risk of personifying machine learning too much. But here you have an overview, so you can get an idea of potentially semantically meaningful concepts. So you have different concepts. Okay, we have some vegetables, we have some plants, we have animals. And if you want to see more, you just click into that. So for example, if I want to click into these animals in this fruit section, I can click into that and it will directly zoom into there. If I want to continue, I want to look at these sea animals, I can click into that node. So really the dynamic is that we have some preview of a cluster and then we could go into it, which sort of achieves the scalability part of it and doesn't overwhelm the user too much. So I'm going to go back by clicking on the parent node each time. And to give you an idea of what the sidebar has, it's also showing different ways to show the summary. So how far are we really traversing down the tree? We can add more splits to show more detail. But we can also change the image size, which corresponds to showing less images and more of a summary. Or we could go the other way and show a very large number of images. And to give you an example of just looking for maybe a very low metric area that could be problematic, we can just completely focus on those images in a subtle way or just completely focus on that. And you can look through this class table as well, which directly connects you to the DendroMap itself, which gives you other interesting statistics. So in this case, having looked at this beforehand, you can look at different metrics just on different boundaries, which is quite nice that you can't do with a free structure such as t-SNE. So we can click into this, which is mostly humans here, and we could look for varied error-filled clusters. And just from beforehand, by looking at a lot of these, it seems to get the stereotypical gender correct, like boy, man, but it differs by age. So that's some interesting insight that you can directly get from DendroMap. Okay, so getting back to the presentation, we directly compared what I just showed you to what we were building up from before, which was the structure of like local similarity, and to make it very comparable and fair, we also made it a grid structure. So to evaluate this, we want to see from our application, the ML application, is this useful and could it be used compared to this baseline of TSNE? Because a lot of people use that, right? So for tasks such as giving some semantically meaningful description, you would be able to, for example, try to search for that. So that's one of the tasks. Or trying to look for some high metric area. So what we found was that the task results were actually quite similar compared to TSNE. And what's a little bit more promising is that in terms of the observations and qualitatively, we found that it, almost by definition, was better in certain cases where you needed more structure. So some quotes that you can look in the paper as well were that it was a very structured workflow because you got all this other summary information. So you have those numbers, but you also have clear boundaries. For example, I want to look within the vegetables. I could look to that preview, directly click into it, and continue to traverse down that without being overwhelmed by a ton of images. In terms of directly improving what we have here, I think improving the hierarchical representation itself in terms of computation, but also you could think of different interactive ways to refine a structure like this. If you believe that certain images should be in a different cluster, maybe a user could change that and things could update. Or if you knew other information, for example, you did have this nice metadata, you could potentially create a more interesting tree. Additionally, we could also formalize the interactions a little bit, where it would help to just communicate and research, but also just directly on this tree map itself, looking at these different summaries, these can be arranged in different ways. So these images right now have a pretty good clumping structure of similarity, but you could group these by different things like misclassifications, or you could sort them or scroll through them. Okay, so that concludes this presentation. You can go to this link if you want to see this live demo, which I just showed. You can mess around with that. There's a supplementary article and links to all the co-authors. And yeah, thank you.
Thank you for the talk. There are quite a few questions on Slido. Some that have been upvoted are, how do you place images of a cluster to the layout? Do you use some kind of TSNE projection?
No, so we're directly using, wait, are you referencing the TSNE grid or the actual dendro map? Can you repeat the question actually?
Yes.
Yeah.
How do you place images of a cluster on the layout? Do you use some kind of TSNE projection?
No, so we're directly computing the hierarchical structure, hierarchical collaborative clustering. So we get this nice binary tree structure, which, like I showed before, I can go back to this. Let's go here, where you could directly split things across. And the nice thing about, for example, using the slice dice tree map algorithm is most of this is ordered. So you'll be able to very easily order the clusters, and you can just directly visualize the images on top of those in the actual dendro map.
Sounds good. There are quite a few more questions, but I'm going to go probably through two more. So what if images contain very complex semantics, like scene pictures, each with multiple labels?
Yeah, this is a good question. Just from experimentation and looking, for example, for larger data sets, I think most of people are familiar with ImageNet here, right? So ImageNet, a lot of the, just for ImageNet 1K at least, there's a lot of where it labels it some random object in the picture, and it's not even the main object. And just from looking through that, it's pretty difficult just to get an idea of region being semantically meaningful. So I think this is more of a general problem and not necessarily for dendro maps specifically, but if there was more interesting stuff, at least a future direction is trying to understand how many images can we actually understand, and would a summary on each individual node actually be helpful? But that is still an open question. But it could be interesting.
And then there's the last question. You can refer to Slido afterwards to see the rest of the questions. But another one would be, can dendromap be used to investigate the latent spaces of intermediary layers in a large model?
You could potentially do that, right? Because we're taking the representation from some model, then we're clustering those. So there could be a way to compare different layers, and you having different dendro maps between those and trying to see which clusters differ based on that. And even from that, you could come up with a different visualization. But I think maybe you'd have a better bet with just TSNE for that, because this imposes even more structure. And specifically for this case, I don't know if that would be very interesting.
Thank you.
Thank you.
All right, very interesting talk. Let's thank the speaker again. For the last presentation of the session, we have a paper titled Diagnosing Ensemble Few-Shot Classifiers, and the paper will be presented by Wei-Kai Yang from Tsinghua University.
Hello everyone, I'm Wei-Kai Yang from Tsinghua University. Today, I'd like to introduce our work, Diagnosing Ensemble Few-Shot Classifier. Few-shot classification aims to train a classifier with very few labeled samples, and that's what we call shots. A promising way to do that is the learners will process these images and measure the similarities between images, and the prediction is made based on the similarities between the sample and the shots. For example, this sample X will be classified as Y3 star, since it looks very similar to X3 star. From this process, we can see that the quality of learners and shots are the key factors of success to few-shot classification, including some poor performing learners or low representative shots will hurt the performance of the ensemble model. Therefore, the key challenge is how to select high-quality learners and shots that can produce good classification results. For learners, first, they should be well-performing. In addition, they should be diverse because combining multiple identical learners do not help improve the performance. But they also need to be cooperative so that they do not introduce too much contradiction and harm the performance. For shots, we will need to remove those shots that cannot well represent their class and add necessary new ones. However, manually tuning the selection is a tedious trial-and-error process, so we develop our visual analysis tool to facilitate this process. First, both tasks aim to find a small representative subset from a large data collection. So we formulate them as sparse subset selection to automatically recommend learners and shots. However, the recommendations are not always perfect. For example, a learner that only predicts some samples with high confidence may be recommended because it is mistaken as a well-performing learner for those samples. Therefore, we develop a visualization to explain the recommendation results and facilitate the interactive tuning of the selection. Here comes the system overview. Given a set of learners which can be extracted from the public available pre-trained model, for example, downloaded from PyTorch or TensorFlow, and given a set of unlabeled samples and shots, the sparse subset selection module automatically recommends a subset of learners and a small set of representative shots, and they are used to build an ensemble model. Next, the matrix visualization illustrates the performance of the learners and helps adjust the selection. Users can also examine the quality of the shots in the scatter plot and replace the low representative shots with the high representative ones. After these adjustments, the recommendation can also be updated, and users can start a new round for analysis. Next, I'd like to introduce the sparse subset selection module. If we had defined the representation cost between each element Ui and each element Bj, sparse subset selection can find a small subset of U that can represent V best. Given a subset A, the representation cost will be the sum of the minimum cost that represents each Vj using the elements in subset A. To penalize a large subset, we add a sparsity term, which is defined as the size of the subset. Using the binary variable Zij to indicate whether Ui is used to represent Vj, we can rewrite this formulation. Then we relax them to a continuous optimization program and solve it using the ADMM framework. We then extend it to recommend learners and shorts respectively. For more details about this part, please refer to our paper. We then conduct a quantitative evaluation to see whether the recommended learners and shorts can improve the performance of future classification. The results show that using the recommended learners or shorts alone can boost the performance, and combining them can further improve the performance. Next, we introduce our visualization that facilitates understanding and interactive improvement of the selection. In sample view, we use T-SNE to project the samples to facilitate the exploration and adjustments on shorts, since it is easy to implement. Here we focus more on the learner view. The learner view aims to help users examine each base learner and make adjustments. The first issue is that we do not have ground truths to evaluate the performance of each base learner, so we compare their prediction with the ensemble model. We design a matrix view. Here, each row represents a learner, and the first column encodes the overall differences on the prediction, and the remaining columns encodes the prediction differences on different classes. In each cell, we use the Venn diagram to represent the samples. The first set represents the samples that are predicted as the classes by learners, and the second set represents the samples that are predicted by the ensemble model. The second issue is the scalability. When there are too many learners or classes, we group similar ones together, and users can freely explore them and adjust the clusters. Here, I would like to show a case study on handwritten digits classification. I will introduce two steps in it. One starts from analyzing the learner, and the other one starts from analyzing the short. 4 learners are recommended by the algorithm. Among them, BL Tier 6 has the largest prediction difference from the ensemble model. We first analyzed these learners and found that 3 regions have a larger drop in prediction confidence. We select these samples in the region and found that many samples of 3 and 5 are misclassified, and there's no short of 3 and only 1 short of 5. So we decided to recommend more shorts in these regions and add shorts of 3 and 5. Our system can also recommend shorts globally. 2 low-quality shorts are recommended to be removed. Their poor coverage indicates they are not representative. 3 samples are recommended as shorts to be labeled. By adjusting the learners, removing 2 low-quality shorts, and adding 13 new ones, the accuracy is improved from 0.497 to 0.707. To conclude our work, we developed a visual analysis tool for visually diagnosing an ensemble feature classifier. Our method includes 2 subject selections for recommended learners and shorts, and we developed the learner views and sample view to facilitate interactive improvement. In the future, we plan to generalize the learner view to other tasks such as object detection, and improve the efficiency of sparse subject selections to handle millions of samples. For more details and the materials such as code, videos, and slides, please refer to our report. Thank you, and I'm happy to take any questions.
Hi, can you hear us okay?
Yes.
Excellent. Okay, we have some questions on Slido.
The results look like selecting appropriate shots is more important than the right models. Did you notice some criteria for good shots, like the number of shots or their diversity?
Yeah, that's a very good question. And then, in fact, we found that the diversity is more. It is true that the shots is much more important than the right model because we have very few shots, and then so increasing the number of shots can greatly increase the performance of the model. But if we have the same budget, we would need to select the more diverse shots, and then so that they can cover all the cases, and then to help the model make the good predictions.
Sounds good, thank you. And another question popped up in Slido. If you are computing and showing several shots for the analyst to choose from, why not use all those shots for learning? What is the benefit of using less data for training if it is already available?
As I have introduced in the slides, that there are some kind of low quality shots that may harm the performance. For example, it looks very like class A, but it is actually class B. And then if you include some disambiguous shots, and they will confuse the model too, so that the model may not recognize the class correctly.
Thank you. And the last question is, you separate the process into two stages of model selection and shot selection. However, do you see any impact between these two stages affecting each other?
Yeah, actually, we have done some experiments that we first select shots and then select the models, and then we also change the order, and then the performance does not change too much. And then in our implementations, we think that the shot selection should be carried out first, because we can leverage all the similarity measures learned from all the models, and it will be more robust.
All right, thank you very much. Let's thank the speaker again. All right, that concludes our session. Thank you everybody for attending, and have a great lunch. Bye.